Hello everyone and welcome to the first official lecture of the online learning series. So today we are going to start material for the last exam, exam number 3. Couple quick announcements before we get going. So this is lecture number 19. For those of you who didn't catch it, lecture 18 is posted. It's optional material for exam number 2. But now we're getting back to required material. So for those of you who didn't catch this already, exam number 2 is going to be on Newton's laws, energy momentum, so chapters 5 through 8. That was going to be done online through e-learning. It'll be Thursday through Saturday of this week. And so I've already posted a practice exam on e-learning. I've already posted some practice problems on mastering physics. The big thing I want everyone to do, if you haven't already caught this, is please go take the practice exam on e-learning as soon as you get a chance. So it's formatted very similarly to the way I'm going to format the actual exam. And basically, if there's any issue with taking the exam, I want to know right now so that we can anticipate that before you take the real exam. If you let me know, I'm going to be very flexible. I know we're all going through an unusual situation here, but if you give me a heads up, I'm happy to do what I can to see what we can do to make this guy work. So that's what's coming up. Unfortunately, due to the timing of how all this spring break and similar works actually was already going to be happening even before COVID. Today and Thursday will be material not for exam 2, but for exam number 3. So we're moving on to chapter 9, which is rotational motion. It'll be somewhat short lectures. I'm not going to go too intense. And actually, homework 9, instead of being due next Monday, we'll have that due next Wednesday, just to give you guys a little extra time to play catch up and to start getting used to this new system. So, without any further ado, let's start talking about rotational motion. So to date, we have mostly been talking about what I would call translational motion, which is basically I have an object, I throw it, I kick it acts on a spring, it's moving in a straight line, generally speaking. But of course, sadly, the world is not a one-dimensional place. I don't just get to use my single equation. Eventually, I have to deal with the complexities. And one of the big complexities that you all are certainly aware of is that objects not only can move, but can also rotate. So for example, consider the compass wheel that you can see over here on the right-hand side of the screen. That compass wheel has some needle, let's say, that's able to move around. And so if I want to describe the rotation of a compass needle, the rotation of an ice skater as they're undergoing a spin, the rotation of any solid object, what's called a rigid body, I need some way to describe that. And so the way I'm going to describe that is by two different quantities. One is the angle, theta, about which it rotates. So this should be pretty straightforward. If the compass needle starts out here and then rotates some amount theta here, that angle theta is going to tell me how far it's rotated. Pretty straightforward. We'll use the usual way of denoting theta, which is it's the amount that I rotate off of the x-axis. So if in doubt, it's kind of the usual way I'm going to define theta, is the angle off of the plus x-axis. And then the one thing that I want you to remember is if I want to specify how an object is rotating, I don't only need to specify how far it's rotated, the angle, I also need to tell you the axis about which the rotation occurs. This is a little hard to indicate on the slides, but going back to our camera, imagine I have my, what do I have here? Mug. My mug here. My mug can rotate about the z-axis, or if I call this guy the x-axis, it can rotate about the x-axis. Let's hope there's nothing in there. Y-axis, and so on. So rotation specifies an angle, the total amount that it rotates, and an axis, which tells me around what direction it is rotating. The axis is the line around which it rotates. So this is the first most important thing that I want to remind you. Whenever you're specifying rotation, always remember to define your rotation axis. Failure to do so will result in problems down the road, one of the most common mistakes I see on exams. The other caveat that I want to mention is that whenever we start working with rotational motion, let me just basically say, from here on in the course, with the exception of exam 2, we always want to use our angles in radians. When working with rotational motion, please always use theta in radians. And the reason for this is very straightforward. Radians are the right way to express angles. If we were to go back and reinvent math, we would just start from radians from the beginning. But since we can't, here we are definitely going to want to use radians because we're going to want to do some calculus. And also because there's this beautiful formula, S equals R times theta, which tells us that the distance I move, the arc length, which is denoted by this blue curve here, is equal to the radius of the circle times theta. So arc length is equal to R times theta. And that's really important because I'm able to connect linear distance, arc length, to angle, theta. And that only works if theta is in radians. All right, so specify your angle in radians, specify your direction, and then you can specify everything you want about the motion. Now, I want to go back to one of the first examples we talked about when we were talking about motion, which was Usain Bolt running around a track. So he did 100 meters, we plotted x versus t, and we got velocity, acceleration. We did all that. Now, imagine, as is actually reality, Usain Bolt running around a circular racetrack, or at least, some racetrack that's not just a straight line. So particularly, let's talk about a circle. And previously, as Usain Bolt was running, I specified his position by, where he was in the x direction. So x equals 0, x equals, 1 meter, whatever, as he moves along. Here, when I'm running on a circular track, I could also just specify his position by the angle theta. So here theta equals 0, here theta is, pi over 10, something like that. And as I go around, the angle theta tells me where I am along the circle. So the idea is as follows. If I want to tell you everything about this motion, what I should tell you is the angle theta, which, by the way, is completely equivalent to telling you how far he's traveled, because theta is equal to s divided by r. So the right way to think about theta, I will sometimes actually use this terminology, is theta is like the angular version of position. It tells me the position along a circle. So if you think of theta as like a position, like x, what we're going to see, what I'm going to really emphasize throughout this lecture, is that all of rotational motion is just 1D motion in disguise. It really behaves identically to one-dimensional motion, with the caveat that instead of talking about real position, x, I'm going to talk about angular position in quotes, which is theta. Okay, so before we go into more detail on that, there's one other thing I want to mention about this angle theta. So if I really want to be a correct mathematician or physicist, the way I should really think about this is as rotation being a vector. So theta written as a vector. And if I want to define the rotation vector, the way I'm going to do that is I'm going to have theta's magnitude tell me how far I've gone. And the direction is not going to specify how I've moved. So the direction of theta is not something like this because it's moving up. It's the rotation axis. Okay? So the direction of theta as a vector is the rotation axis. So for example, if we consider this compass needle that we have over here on the right, sorry about that. So this compass needle example that we have over here on the right, what's happening is this compass needle is rotating within the XY plane, meaning that the axis it's rotating around is actually the Z axis. And here, as we'll discuss in a couple of slides, this is most appropriately thought of as the plus Z axis. So if I'm rotating by some angle theta about the plus Z axis, the way I would express that as a vector is that theta vector is equal to 0 in the x direction, it's not rotating around x, 0 in the y direction, it's not rotating around y, and theta in the z direction. So here's the proper vector way of thinking about rotations. Now, why do we care about that? We care about that because now we want to describe motion, time-dependent theta. And so once I start to do that, I need to introduce velocity. And in particular, as an angle changes, I am going to specify the rate of change by something called the angular velocity. So the angular velocity is denoted omega subscript z, and it is simply defined as the time derivative of theta. Omega z is d theta dt. Now, as we'll talk about what this omega z means in a couple of slides, it's the z component of the omega vector. It's a kind of preview. But if we want to talk about omega as just a number, a scalar, we need to talk about what its direction is, whether it's positive or negative. Oopsie, I see there's a mistake on this slide. This should read less than. Sorry about that. I'll correct that before I post it online. So let's talk about the direction. We are simply going to define counterclockwise. If I look at a usual rotating coordinate system, so I define theta as being positive when I rotate in a counterclockwise direction from the x-axis, that means that theta is increasing when the object is moving counterclockwise. So for an object that is rotating counterclockwise, theta is increasing with time and omega is positive if the object moves in the counterclockwise direction. Similarly, if the object is moving clockwise, then theta is decreasing as a function of time. So if omega is positive, that means counterclockwise if I'm looking down on the object like this. And if omega is less than 0, that means counterclockwise. So now coming back to what I was saying a second ago, the right way to think about this again is as a vector. So if I define theta as a vector, then omega vector is equal to d theta vector dt. And this should remind you of something. It should remind you of velocity. Velocity is equal to dr dt. So again, this is the important analogy between linear motion and circular motion. The math looks identical between these two. And this will also really help us to understand what it means to talk about omega as a vector. So it's defined as d theta vector dt. And if I want to think now about the direction of this vector, so the magnitude is the magnitude of d theta dt, the direction of the vector is defined basically by the axis of rotation. So we'll always be pointing along the axis of rotation, either in the direction of theta or opposite the direction of theta. Now, in order to make this a little easier, we're going to define a right-hand rule. There's a nice right-hand rule for how to do this. What you want to do is you want to imagine the object is spinning. And what you're going to do is you're going to take your fingers. So I want everyone to take their fingers, point them straight out with your thumb pointing up, and then curl your fingers in the direction of the rotation. So for example, if I look at this gear down here, I'm going to curl my fingers in the direction shown in the picture, and you'll notice that the thumb is pointing straight up. The direction of your thumb on your right hand, it's a right hand rule, tells you the direction of the angular velocity omega. Similarly, if I were rotating clockwise down here, I curl my fingers in the direction of rotation and my thumb points down. Now when I wrote omega z is greater than 0, what that means is that the z component of omega, which is like the amount of z along the z-axis here, so omega along the z-axis here, is positive. So notice here, when I had counterclockwise rotation, my omega is pointing up. So that says the z component of omega is positive. Similarly, for clockwise rotation, omega is pointing down. That says the z component of omega is negative. So, if I can define velocity, it will not surprise you. I can define acceleration. I take one more derivative, and the rate at which angular velocity changes is called angular acceleration. Angular acceleration is denoted alpha subscript z. Z here again refers to the direction of the rotation. It is by definition d omega dt, or d squared theta dt squared. Apologies on that as well. I'll fix that online. Alrighty. So, again, if we think of these as vectors, it makes perfect sense. I take one derivative of omega, I get angular acceleration, or that's two derivatives of theta written as a vector. And I could go on and on. But the important thing that you should have noticed is that the math here between one-dimensional motion, v equals dx dt, a equals dv dt, for example, and rotational motion is identical. The only difference is that everywhere I have an x, I need to replace it by theta. Everywhere I have a v, I need to replace it by omega, the angular velocity. And everywhere I add acceleration, I replace it by angular acceleration alpha. Technically alpha z if I'm being a little bit careful. So we can use all of the formulas that we already know for one-dimensional translational motion. So here you go. Here are the formulas I taught you. V is dx dt, x is the integral of v dt, v is integral of a dt, and then these set of formulas down here only work in the presence of constant acceleration, as you are very familiar with. So now, if I want to talk about rotational motion, all I have to do is replace x by theta, v by omega, and so on. So for example, delta v equals a delta t, v becomes omega, a becomes alpha, and t just stayed alone. Time is still time. So all of these formulas, you don't need to relearn them. They just behave exactly the same way. I'm just changing the definitions of my variables. So now let's go ahead and start getting some practice on this. So imagine after winning the world championship, Usain Bolt's going to run a victory lap. But now we'll go on that circular track. And in fact, he's not just going to run in a big loop. He's going to run back and forth, I don't know, high-fiving a bunch of people, whatever he's doing. And what I'm going to tell you is that the angular position theta as a function of time is described by the following graph. All right, so where on this graph is his angular velocity omega z equal to 0? Labeled 7 points here, A through G. Where is his angular velocity omega z equal to 0? So take a quick second, write down what you think the answer is. And now let's see what's going on here. So what we do know is that omega is the derivative of theta. If the derivative is 0, derivative again means slope, so that means the slope is 0. And there are 2 points on this graph where the slope is 0. At point B, it's a maximum, the slope is 0, and at point E, it's a minimum, the slope is 0. All right, so now let's continue on to part B of example 1. Where is his angular acceleration alpha equal to 0? Again, take a quick second. Which of these points has alpha equals 0? All right, well, this one's a bit trickier and admittedly not as well drawn as the previous one, but let's see if we can do it anyways. We know that alpha is d omega dt and omega is d theta dt. So alpha is the second derivative of omega. And the points where the second derivative is equal to 0 are known as inflection points. So they're points where the curvature goes from negative to positive. So where on this graph does the curvature go from negative to positive? Well, roughly speaking, it's at this point D. You can see it goes kind of negative curvature here, positive curvature there. Squint a little, and the answer to this part is D. What is the direction of omega vector at point C? So first off, is it x, y, or z? Forget positive or negative. Is it x, y, or z? Okay, so it's z because all of these rotations are happening around the z-axis. If I don't tell you anything else, we should just generally assume that rotations are happening around the z-axis, and therefore the direction is either going to be positive z or negative z. To figure out whether it's positive z or negative z, again, let's go to this formula. Omega z equals to d theta dt. So that's the z component of omega is d theta dt. d theta dt is just the slope of this graph. And notice that at the point C, the slope is negative. And therefore, omega is in the negative, or now omega z is negative, omega is in the negative z direction. Finally, what's the average angular velocity between A and G? In order to give you some numbers, let's say, I don't know, t equals 0 here, 1 second here, and let's say that I'm going from approximately, I don't know, 2 pi radians up here and negative 2 pi radians down here. So get an approximate number for the angular velocity, average angular velocity between points A and G. Okay, so this one's a little bit trickier. You have to remember back to your formulas. Again, all of these formulas are identical to the formulas for linear motion. And so in particular, the formula that you hopefully remember is that the average velocity is equal to dx delta x over delta t. Here, average angular velocity, omega z average, is equal to delta theta over delta t. And for this particular problem where I'm going from points A to G, meaning final is G and initial is A, you'll notice that they're exactly at the same value of theta, so delta theta is equal to 0, which means the average angular velocity is just 0. Okay? Good. Let's do a few more numbers. So now, imagine that I have cars which are braking. So car brakes, the way they actually work is your tires are spinning, and what it's going to do, it's going to apply friction to a part of the wheel, your brake pad I think it's called, but perhaps someone can correct me. So let's just imagine that that produces a constant angular acceleration that's opposite to the sign of the angular velocity. So again, exactly like linear motion, if I produce an angular acceleration opposite velocity, that means I'm slowing down. Okay? So let's imagine this angular acceleration is negative 10 radians per second squared, and the initial angular velocity is 20 radians per second. Notice that the units of angular velocity are radians per second because it's theta, which is radians divided by time. So radians per second, and similarly for angular acceleration. All right, so I want you guys to take a few minutes, write down your answer, pause the video if you like, and once you think you have it, let's see if we can get the total time that it takes for the car to stop, in other words, for the wheels to stop, and the number of revolutions that the tires undergo before they stop. Alrighty, so I will assume that you've done the problem at this point. Let's go ahead and go over this answer together. So what are we given? We're given a constant angular acceleration alpha z, which is negative 10 radians per second squared. Notice that radians are unitless, so I could also just write this as 10 seconds to the minus 2 radians per second squared, and just per second squared, they're the same thing. I'll do that a lot, but it doesn't really matter. I could also write this as negative 10 radians per second squared, same thing. I'm given an initial angular velocity in the z direction, so an initial angular velocity of 20 radians per second, positive. And what's my final angular velocity? 0, right? When I'm done, I come to a stop. So I'm given constant angular acceleration, omega z, omega final. And part A of the problem, let's go back to it, ask me for how long does it take to stop? In other words, what's the delta t that it takes to stop? So this is a pretty straightforward formula. We have for constant angular acceleration, only for constant angular acceleration, we have that delta omega z is equal to alpha z delta t, exactly like delta v is equal to a delta t. We know everything in this formula except for delta t. So let's divide through by alpha z, solve for delta t, and what I get is delta t is equal to delta omega z, so that's omega z final minus omega z initial over alpha z. Final is 0. And that's negative 20 radians per second divided by negative 10 radians per second squared. And when you plug in some numbers, this is just 2 seconds. So it takes 2 seconds to solve. Now, part B of the problem asks, how many revolutions do the tires undergo before they stop? So let's translate this. How many revolutions? What that's asking about is what's the angle it goes through, right? So one revolution, and this will be a very important formula to remember, one revolution of any circular motion is just 2 pi radians, right? Because that's like going around the circle once. One revolution is 2 pi radians. So in this case, what it's really asking for in physics speak is delta theta, expressed in the units of revolutions. All right, so we whip out our handy-dandy formula book. In this case, we had a previous formula, delta v squared is equal to 2a delta x. You may remember this one. That becomes delta omega z squared is equal to 2 alpha z delta theta. And again, I want to solve for delta theta. So let's divide both sides of this equation by 2 alpha z. And I get that my angle that it goes through, delta theta, is equal to delta omega z squared over 2 alpha z, which is omega z final squared, minus omega z initial squared, over 2 alpha z. Omega z final was 0. Omega z initial was 10 radians per second, and alpha z was negative 20 radians per second, or I think I had that backwards. Anyways, you plug in some numbers, and the answer turns out to be 20 radians. So we're almost done. It goes through 20 radians before you're stopping, but the problem asks how many revolutions. So now I just need to do a quick unit conversion. So delta theta is 20 radians. And now what I've told you is that one revolution is 2 pi radians. So all I need to do is I multiply by 1 revolution divided by 2 pi radians. So multiply by 1, radians cancels, revolution stays, and 20 over 2 pi turns out to be 3.18 revolutions. So that's how far it goes before it eventually comes to a stop. We'll do one more example of this before we move on to talking about the connection to linear motion. So it's a bit more complicated of an example, but again, it's within the context of what we learned in 1D motion. So imagine at t equals 0, a grinding wheel. For those of you who aren't familiar, this is something that you would use to, for example, grind down an axe, something like that. So a big sandstone wheel. Starts out with an angular velocity of 24 radians per second. Has a constant angular acceleration of positive 30 radians per second squared until it goes way too fast, trips a breaker at t equals 2 seconds, and then it winds down, basically. It stops over some amount of time, and during that time, it goes 432 radians, imagining that it goes at a constant negative acceleration. All right, so what I want you guys to take a few minutes, try to do this yourself. Ask, what's the total angle it turns through from the beginning to the end? What's the time that it reaches, that it eventually stops? And what is this mysterious angular acceleration that it has as it's slowing down? So take a couple minutes here. Good. I will assume that everyone did the problem. If you forgot to pause the video, now's a good time to pause the video. All right, so let's go over what's going on here. First off, I like to draw out these types of problems. So we're going to go ahead and draw this out, starting from angular acceleration, because that's the easiest, as you'll see. Again, if there's nothing else you take away from this class, remember, if in doubt, draw it out. So what do we know? We know that we start at 30 radians per second squared as a constant angular acceleration. And because I like to put symbols on everything, we'll call that alpha initial. And then eventually, at some point in time, 2 seconds, I trip a breaker and it goes into a constant deceleration phase. So we'll call that alpha final. And we don't know what alpha final is. But we can guess it's negative because it has to eventually come to a stop. And then finally, at some point in time, it comes to a stop. We'll call that TS for stop. Okie dokie. How about angular velocity? So if I told you this is the angular acceleration, I encourage you, see if you can figure out what is the angular velocity as a function of time. All right, so here we go. We start out, as is stated in the problem, at 24 radians per second. Let me go ahead and redraw this. Sorry about that. 24 radians per second. And I start off at a constant positive angular acceleration. So remember, with constant acceleration, I just increase my velocity linearly. The slope is constant, up to some final value. We don't yet know this, though we're going to be able to figure it out pretty easily. But at 2 seconds, a breaker trips. Then, it's going to crash down. It's going to crash down at a constant negative slope, alpha final. Until at some point, TS, what value of omega does it reach? 0. Right? So at the end of the day, it comes to a stop. That's T stop, TS. Omega is equal to 0. So there's my alpha, there's my omega. By Greek standards, that's God. Is that a good joke? Probably not. Well, I won't be able to hear the lack of laughter, so I'm just going to go ahead and move on with my life. Final thing. Theta. I'm sure a number of you are thinking, you lucky stars, you don't actually have to hear too many more of my jokes in person. All the little things, right? All right, so let's say a little bit about what's going on with theta as a function of time. So theta is, generally speaking, a parabola. It's constant acceleration. I start off, let's say, at theta equals 0. I can just pick theta equals 0 to be my starting point. I then accelerate, starting at a constant slope of 24 radians per second and then actually increasing. So up to some time t equals 2 seconds. I have this increasing parabola. Then a breaker trips and I decelerate. So kind of here's the tripping of the breaker. I continue along. I decelerate and eventually I come to a stop, meaning my slope hits a 0 value. So this is t stop when I'm done at the end of the day. Now, I do know one other piece of information, which is why I like to draw this graph, namely that the amount of theta between when the breaker trips at t equals 2 seconds and when I end at t stop is 432 radians. And that's going to be, of course, important. So keep that in mind as we're solving the problem. Okie dokie. So part A of the problem, what we want to do is we want to solve for the total amount of angle that we undergo. And in fact, we already know quite a bit of this. We know the 432 radians that we have at the end of the day. So now all we need to know is what's this delta theta here during this initial acceleration period. So during the initial acceleration period, I know almost everything. I know, so during the initial period, I know my initial time. Let's call that TA. A is right at the beginning. B is at t equals 2 seconds when the breaker trips. And let's call it S for stop, is at the end when everything stops. Okay? So TA, my starting point is 0. Theta A, my starting point, is 0. Omega ZA, my angular velocity, is given. It's 24 radians per second. And then when the breaker trips, I'm told the time. So TB, in this case, is 2 seconds. And throughout this process, I know I have a constant angular acceleration, alpha z, which is, 30 radians per second squared. Okie dokie, so constant angular acceleration during this period, and what I'm after is delta theta, or in other words, theta b. So let's go ahead and use the annoying one. Delta theta is equal to 1/2 alpha t squared plus omega 0, which in this case is omega za times delta t. But I know all these numbers. As stated above, when I plug them in, it's not so bad. I actually get 108 radians. So during this first little bit, I now know that I'm turning 108 radians, and I turn another 432. So the total angle that I go through is 108 radians plus 432 radians, and that is 540 radians. Woohoo. Okie dokie. Part B starts to get a little trickier, but not too bad. So part B, now we want to know, where are we here? At what time does it stop? So again, I know part of this. I know that I start off during the second period at 2 seconds, and I end up at TS. So the question is, what's this TS, the time that I stop at? All right, so what do I know about the second period? Well, I know I go through 432 radians. I know my initial angle, but that's not so interesting. I know my initial time, but that's not so interesting. I don't know alpha, so I can't use that. And this is not quite enough information to get a time. So I'm going to need one more piece of information if I want to do that, which is this omega value here, which here we're going to label as omega b, because that's my angular velocity at this point b where the breaker trips. So let's go ahead and solve for that. Again, using the same piece of information as part A. So now, again, during this initial period from time A to time B, I also have that delta omega, z, is equal to alpha delta t. I know delta t is 2 seconds. I know alpha is whatever it was, 30 radians per second squared. And now that's going to let me solve for omega b. So delta omega is final, which is omega zb, minus initial, which is omega za. That's equal to alpha delta t. I bring my omega z over to the other side. Solve for omega zb. And that turns out to be there we go. 84 radians per second. So now I'm cooking with gas, because now I know almost everything about this period between when I hit the brakes and when I stop. I know the initial velocity, I know the final velocity, I know the initial time, and all I need to now know, and I know how far I go. And now I just want to solve for the time. So in this particular case, I'm going to use the formula that's pretty rarely used actually, but it does in fact work here. Namely that delta theta is equal to omega initial, which is b, plus omega final, which is the stopping point, over 2 times delta t. Remember this one? The average velocity is equal to delta theta over delta t. So we know that I stop at 0. We know omega b is 84 radians per second squared, radians per second, and I want to solve for delta t. I know that delta theta is also 432 radians. So delta t is equal to 2 delta theta over omega zb. Plug in some numbers, that turns out to be 10.3 seconds. And if I add that to my original 2 seconds before the breaker tripped, my total time, which is TS in this case, is 10.3 plus 2, or 12.3 seconds, between when I start this experiment and when it stops. And last little bit, now I've given pretty much everything. I know almost everything about this problem. The question now asks, what is this mysterious acceleration? Let's call it alpha final. So for this one, I'm just going to use between the periods B to C when it's decelerating and has alpha final as a constant acceleration. I'm going to use delta omega is equal to alpha delta t. I know everything in this formula except for alpha, so I'll go ahead and solve for alpha by dividing through by delta t, and then I get that alpha final z is negative 8.16 radians per second squared. So again, the thing that I'm trying to emphasize here is that once you start rotational motion, I mean, it's not explicitly more fun, but it's no worse than working with one-dimensional motion. This is very similar, for example, to these various problems we solved where a car would accelerate for a little bit and then slam on its brakes and decelerate to a stop. You have multiple periods of acceleration. You use the same machinery, the same math. Really, it's basically the same physics in disguise, and you can solve these types of problems. So rotational motion does not need to be harder than translational motion. If, on the other hand, you did not love that part of translational motion, I have bad news for you, which is it's coming back to haunt you. So if you did struggle with constant acceleration, with free fall, with those sorts of problems, now's a good time to go review that math, bone up on how it worked there. We're going to basically just be using it again here in a slightly different context. So that's what I wanted to say about rotational motion by itself. But the cool thing is that rotation is actually connected to translation. So it's this formula I was saying before, arc length is equal to r times theta. So consider that I have, Usain Bolt running around a track or some point, like, I don't know, a pendulum is swinging around my head. I have a point at a radius r that is moving around in a circle. And I'm going to specify this motion by theta. So the distance that object moves, let's say Usain Bolt starts here and ends up over here, the distance that he moved is the arc length, s, equal to r times theta. So there's a natural connection in rotational motion between rotation, theta, and distance, translational motion, s. And this is going to carry into all of our other formulas. So I take one derivative, I get velocity. Velocity is ds dt, that's dr theta dt, and the r factorizes, so this is just r times omega. Velocity for motion in a circle is just r times omega. Similarly, acceleration is going to be dv dt. So dv dt is r d omega dt is r times alpha. Acceleration is equal to r times alpha. Now this is tangential acceleration. You may remember, for circular motion, there are two types of acceleration. There's the acceleration around the circle in the direction of the motion. That's called tangential acceleration. And then there's the acceleration towards the middle of the circle. That's called centripetal acceleration. So alpha, the angular acceleration, is actually connected to tangential acceleration. And centripetal acceleration doesn't change at all. It's still going to be v squared divided by r. The new thing is that now I can plug in v equals r times omega, and I can rewrite this as just omega squared times r. So tangential and centripetal acceleration now both exist. And now we actually have a formula for them. For those of you who were, I don't know what's the word I'm looking for. For those of you who stayed for my little calculus tutorial, you may vaguely remember this when we talked about circular motion way back when. We can actually see this directly from the calculus. And for those of you who don't remember, you can go revisit my notes. You'll see that basically this math is there. Now we can put a name to it. Angular velocity and angular acceleration. All right, so this is the connection between translational motion and rotational motion. S equals r times theta, and then these various other formulas that you get from taking a derivative. V equals r omega, and so on. All right, so let's go back to our car. Our car was moving along, slammed on its brakes, and came to a stop. So imagine the same situation. I slam on my brakes, my angular acceleration of the wheels, or the tires, is minus 10 radians per second squared. The initial angular velocity was 20 radians per second, and the radius of the tires, I'm going to now tell you, is 0.343 meters. So looking back over the solutions we had to those previous problems, what I want you to try to figure out is what is the total distance it takes for the car to stop, and what's the initial translational speed of the car. All right, so hopefully everyone has paused me at this point, solved the problem, and now let's go ahead and go over this answer together. All right, so we are talking a car undergoing uniform negative acceleration. Alpha z is negative 10 radians per second squared. And we know that the initial omega z is, what did I say, 20 radians per second. I know the radius of the tire is 0.343 meters. And as a quick reminder, the total distance that it went, the angular distance it went, I should say, was 20 radians. Okay? So my delta theta is 20 radians. And now what we want to know is we want to know how far it traveled in this time. So here is where we're going to use this nice formula that connects distance to angle. So in particular, what we know is that the total distance traveled when I go in angle theta is r times theta. And here the angle is 20 radians. The radius is 0.343 meters. So I just multiply 0.343 meters times 20 radians. And I find that when I slam on my brakes, it takes a total of 6.86 meters to stop. Notice that this was very easy because my theta was in radians. Radians don't have any units, so I don't have to worry about them. If I'd had them in degrees, I'd have a problem. So you want to be really careful about that. Similarly, part B of the question asks, what is my initial velocity, linear velocity? So notice that my linear velocity is just r times omega. A point on the edge of the tire is moving as fast as the car, of course. And so now I just plug in r is 0.343, omega is whatever it was, 20 radians per second. And it turns out I actually also get 6.86, but now my units are meters per second because this is a velocity. And there you have it, folks, the connection between angular position and actual position, or angular velocity and actual velocity. So we're going to use that a lot later. It's something I really want you to keep in mind. There's one more challenging problem that I'm going to give you guys today, and then we're going to talk a lot more about applications of this in the next lecture. So consider the following situation. A discus thrower is going to move the disc in a circle of radius 80 centimeters. And so since you all have YouTube access, go find a discus thrower if you've never seen it. The way these guys work is they start out at rest and they do this crazy spinning thing until eventually they release the disc and it goes flying and they win lots of medals. So imagine the following. I'm going to imagine this guy is holding the disc within the, let's call it the XY plane. So we'll call the plane of the board here the XY plane, meaning that he's rotating around the z-axis as usual. And at a particular instant of time, I'm going to imagine an angular acceleration of 10 radians per second, angular acceleration of 50 radians per second squared. What I want you to figure out is what is the centripetal acceleration, magnitude and direction, tangential acceleration, magnitude and direction. And if he releases at this point from a height of 1.5 meters, how far does it go? All right, so hopefully everyone's had a shot to do this. I'm going to take a picture because it's just fun, and I can do that on my fancy iPad. So let me see if I can make this work. I go into here, create a new thing. Please, please, please. This is why old people shouldn't be allowed to use technology. Here we go. Come on. Oh dear. Well, it didn't work. Someday. Anyway, so I have to redraw this by hand. All right, let's see if we got this. Here's my disk. It has an angular velocity, omega z, which was equal to, what was it? 10 radians per second. At the point in time that was drawn in the figure, you may remember it was passing just through the negative x-axis. The radius, I'll call that lowercase r, was given as 80 centimeters or 0.8 meters. And at this particular point in time, it's also accelerating, so he's speeding up, with alpha z of 50 radians per second squared. Okay, so that's the rotational motion. And the question asks, what is centripetal, tangential, and total acceleration? So let's start out with centripetal acceleration. We know the formula, centripetal acceleration is equal to v squared divided by r. And since I'm lazy and don't want to plug in to solve for v, I'm going to use this second formula, that it's omega squared times r. So those are, again, equivalent formulas. This one's just a little easier. So here I can plug in. Omega squared is 100 radians squared per second squared, or just 100 per second squared, times radius of 0.8 meters. I get 80 meters per second squared. Again, I just want to emphasize radians are a unitless quantity, and that's why I can just forget about the radians in this expression. Which direction is this going in? So I want you guys to think, is it plus x, plus y, or minus y? Forget about the drawing where it's actually answered already. So this is in the plus x direction because centripetal acceleration always points towards the center, which in this case is the plus x direction. All right, how about tangential acceleration? So earlier we never really solved for tangential acceleration. We just said, it's a thing that exists. Now we can actually put some numbers behind that. So the formula we're going to use for this is that tangential acceleration is r times alpha. Again, remember, alpha always will refer to tangential acceleration, not centripetal acceleration. And again, that's pretty straightforward. That's 50 radians per second squared times 0.8 meters, or 40 meters per second squared. All right, so again, I want you guys to think, which direction is this in? Plus x, plus y, or minus y? The answer is minus y. So it's moving, it's rotating around in a counterclockwise direction as shown. And at the particular point in time, the velocity is pointing down, right? I mean, it's moving down in the negative y direction, and the acceleration is positive. So it's going faster and faster. When the angular acceleration is positive, then the tangential acceleration is in the same direction as the motion. If it were decelerating, tangential acceleration would be opposite the motion. So in this case, acceleration is in the negative y direction. And the last bit of this problem asks, what is the total acceleration on the problem. So the thing to remember here is that acceleration is like any other vector. I can always add up components. And by definition, for circular motion, the total acceleration is just centripetal acceleration plus tangential acceleration. So that's 80 meters per second squared in the plus x direction, plus in a vector sense, 40 meters per second squared pointing down in the negative y direction. That's my total acceleration. And you'll notice that this is just a right triangle, meaning that the total magnitude of acceleration is just the square root of x squared, 40 meters per second squared, plus y squared, 80 meters per second squared. That's all under the square root sign. Plug in some numbers. This turns out to be 89.4 meters per second squared. So there you have it. Now part B of the problem asks, now imagine he throws it, how far does it go? So the key point here is that as soon as he throws it, this just becomes a regular old projectile motion problem that you already know how to work with. So what I'm going to do, I'm going to draw a side view. Here's this discus thrower. Here's the discus. And what he's going to do, he's going to throw it with some initial velocity, and it's going to fall to the ground. The problem asks, what is the horizontal distance that it goes? And here, this is super annoying, but I'll call this distance, I don't know, D, capital D maybe. That is the worst capital D in the world. Let's give it another shot. Capital D. The axes are slightly annoying because, as we just saw, the velocity is actually in the negative y direction, meaning positive y is to the right, to the left. And notice that I've already used up x and y because that's the plane of the board. So I have no choice but to pick z as being my vertical axis, and it turns out, if you're careful, though this won't be particularly important, actually it doesn't really matter at all at this point, I'm going to call plus z up. And so my formulas are exactly like projectile motion, but just now I have slightly unusual axes. So let's talk first about the y direction, because that is what the rotational motion is setting for us. So when he releases it, the thing that we really need to know is its velocity. Remember, the initial velocity is what enters into projectile motion. So what I need to know is the initial velocity of the disk. And the initial velocity of the disk, here we'll just talk about its speed to make life easier, is in the y direction. Well, that's just r times omega. Technically, this is in the negative y direction, but that's not really going to matter here. So let's just pretend it's positive y. And we know all these numbers. We know omega z is, 10 radians per second. R is 0.8 meters. And so it starts off moving at 8 meters per second. Just before it hits the ground, what is the velocity in the y direction? Also 8 meters per second, right? So it's falling in the z direction, meaning the y velocity is constant. In fact, I picked a really weird set of coordinates such that during this free fall period, the projectile motion, the acceleration is actually 0 in the x direction, 0 in the y direction, and negative g in the z direction. So that's unfortunate, but that's life. And what that means, if the acceleration is 0 in the y direction, that means that this is a constant velocity in the y direction. Okay, now let's talk about the z direction. So right after he releases, initial is right after releasing the disk, the velocity of the disk in the z direction, let's call it vz initial, is just 0, right? It's not moving up, it's not moving down, it's moving in the y direction. So the z component of velocity is 0. The z coordinate, z initial, is 1.5 meters. That's the height that's given to us. And the time is, let's just call it 0. It doesn't really matter. Final, right before it hits the ground, we don't know the velocity. We only know the position, z final is 0. It hits the ground, let's call that z equals 0. So I know my velocity, I know z initial, I know z final. That's going to be enough to solve the problem. And so in particular, what I'm going to try to do, I'm going to solve for delta t. The formula I'm going to use for that is delta z is equal to 1/2 linear acceleration, which is negative g, times delta t squared, plus v0z delta t. We said it had no initial velocity, so that's just 0. And now I can solve for delta t. Delta t is going to turn out to be the square root of 2 delta z over negative g. By just rearranging this formula, plug in z final is 0, z initial is 1.5, and it turns out the amount of time that this takes is 0.553 seconds. Now we're almost done. The problem doesn't ask for the time. It asks for the y distance. So the total distance in the y direction is just the magnitude of velocity times time, because the velocity is constant. We know the magnitude of velocity. It was 8 meters per second. Velocity was negative 8, so the magnitude is 8 meters per second. We know the time is 0.553 seconds. We plug in some numbers. It turns out that he managed to throw the disc 4.43 meters, or about 20 feet. So 20 feet? No, 15 feet. So, he's not going to win any awards with this, but you guys are going to learn, hopefully, that rotational motion is not that much harder than translation, and it can be connected to translational motion. So here, the only part where rotational motion played a role in this second part of the problem was here, telling us the initial velocity. Once we had that, no longer am I rotating. The discus is in free fall. And then I can just go ahead and use all of the formulas for projectile motion, which we already know. Okie dokie. So the big takeaway from this lecture is that rotational motion is very, very similar to translational motion. You just have to be slightly careful to use the same formulas and to connect the dots between them in problems like this, where we want to know also about translational motion. Rightio. So just to give you a little preview of where we're going next, I've talked about this mapping, this table, where I can translate all of my one-dimensional motion into rotational motions. Position becomes theta, velocity becomes omega, and so on. The remainder of the next 4 lectures, I think, the remainder of the next 2 chapters, is basically to just do this for every other quantity that you like. Well, every other quantity that you have to know. So for example, I'll tell you that mass becomes a new quantity called the moment of inertia. Kinetic energy is going to become kinetic energy. There's going to be a rotational version of kinetic energy. And then in the next chapter, we'll talk about force. Force is going to become this object known as torque, which those of you who have wrenches are familiar with. And momentum is going to develop into this lovely quantity called angular momentum that haunts physics students and will till the day I die. But I'm going to hopefully tell you it's not too bad. And we will pick up with that next time. All right. So with that, I'm going to go ahead and say, stay safe, be well. Try your best to stay on top of these lectures. I'm not going to try to go too fast. I'm not going to try to do things too much differently than the way class was already going to be. But if you can stay on top of these, treat things like normal, then despite the fact that we are not currently in a normal situation, we'll try to keep these things going as well as possible, learn as much as we can. So reach out to me if you have any questions. Reach out to me if you have any concerns. As we go to online classes, I will do my best to answer them. And let's stay safe out there, do your best, and I look forward to seeing you guys all virtually very soon. Thanks.